Welcome. This video is going to talk about properties of ionic compounds and not only what properties ionic compounds tend to have, but why they tend to have those particular properties. So ionic compounds don't form molecules like we'll find out covalent compounds do, but instead ionic compounds form crystals, or sometimes referred to as a crystal lattice. And it's a crystal with alternating positive and negative ions. And I've got two examples down here at the bottom. On the left, you can see these blue and green ions. The blue happens to be the positive ion, and the green happens to be the negative ion. And if you look, you can see that there's one blue for every green, or one green for every blue. So we would say that the formula or formula unit of this ionic compound is 1 to 1. One cation for every one anion. And my example on the right, you see a view from the top looking down at the crystal or looking from the side. And if you count there, you'll see that there is one orange cation for every two green anions. So this has a 1 to 2 ratio, or a formula unit of, say MgCl2. So how strong are ionic bonds compared to covalent or metallic bonds? Ionic bonds tend to be stronger than either covalent or metallic bonds in most cases. The crystal lattice, or these alternating ions, and then the traction between positive and negative ions forms a very strong bond. So what does that mean? Well, a strong bond means it will take a lot of energy to break this bond back apart. Just like it took a chemical reaction to have this ionic compound formed, it'll take a chemical reaction to take this compound back apart. So the amount of this energy is called lattice energy. And this high bonding or lattice energy is what gives ionic compounds many of their properties. So what are those properties? Ionic compounds tend to have really high melting points. And if you have a high melting point, if you don't become a liquid easily, then you have a really high boiling point. It also tends to make ionic compounds very rigid and hard. Okay, and so think about salts. Sodium chloride is the one that we use a lot, or what we call table salt. It does not easily melt when you're cooking stuff. Sugar, that will melt and burn real easily. Butter melts easily. Salt, not so easy. Other properties of ionic compounds is their conductivity. And it's kind of a weird thing. When ionic compounds are a solid, they're rigid. Rigid means it doesn't move, not much flexibility. So they're going to be poor conductors of electricity because electricity is moving positive or negative charge through a substance. But when ionic compounds are in a liquid, or we say they're in solution, so when you dissolve salt in water, then they become really good conductors of electricity. And in fact, ions are what you're used to hearing as referred to as electrolytes. So when you drink some kind of sport drink, the electrolytes are just ions dissolved in the water. And at that point, they conduct electricity well. And in fact, that's what your body needs them for. Another property to discuss with ionic compounds is the fact that the reaction is almost always what we call exothermic. So exothermic means that the compound will be more stable than the two elements that formed it. More stable means it's going to require less energy to hold NaCl or any other ionic compound together than it does for either element to be on its own. And probably most important to us is exothermic. Remember, exoskeleton means outside. So exothermic means heat is going to be given off when these things form. So an example of this is hand warmers are just iron shavings in a little packet. And when you open up the packet, they can combine with the oxygen in the air to form iron oxide, or what we think of as rust. And that releases heat, keeping your hands warm. That's all there is to them. Just a very simple exothermic ionic compound being formed. Back to lattice energy. We said lattice energy is how much energy it's going to take to break it back apart. So lattice energy is defined as the measure of the energy contained in the crystal lattice of an ionic compound. And again, it tells you how much energy is going to be needed to break apart. In this case, we always compare it to 1 mole, which is a measurement chemists use a lot. But basically, when you compare different lattice energies, you have to be breaking apart the same number of ions, the same size sample. And the amount of energy you get out when you, the amount of energy you have to put in to break it apart is going to be equal to the amount of energy that was released when the compound formed. So the more negative and the larger the number, the stronger the bond is. And that's what lattice energy is really telling us, is how strong is the bond that we're talking about. If the number is bigger, and they're always giving us negative numbers, if the number is bigger, then the bond is stronger. So what makes some ionic bonds stronger than the others? Two things. Smaller ions will have greater lattice energy. How come? Because smaller ions have the valence electrons closer to the nucleus. And anytime you have a smaller atom, it's going to hold on to its electrons more tightly. So if you have small ions side by side, they're also going to hold on to each other more tightly. The other thing that will increase the lattice energy is a bigger charge on the ions, either positive or negative. When that charge increases, it is going to make it more difficult to pull it apart. So just think about the charge, whether it's positive or negative, as being a bigger magnet holding things together. So smaller magnets close together and stronger magnets are both going to increase that lattice energy. So let's look at an example here. Each pair below, which ionic compound would have the greater lattice energy? So either size or charge could make the difference. Well, lithium are each going to pick up a +1 charge, and since it's the same one, the size and the charge on lithium is going to be the same. So lithium isn't really going to be a factor here. Chlorine and bromine are going to determine which one has more energy. They both are in the same family, so they're both going to pick up a -1 charge, so that's not going to determine it. So it must be the size that's going to change. And if we take a look here, if you look at your periodic table, you see that bromine is the bigger atom, chlorine is the smaller atom. So since everything else is equal, LiCl will have greater lattice energy than the LiBr. The next one, NaCl or MgF2, we've got 4 totally different atoms here. So let's start out by taking a look at their charges, and I see that Na will tend to pick up a +1, Cl a -1, Mg tends to pick up a +2, and F a -1. So based on charge, Mg is looking like it will have the greater lattice energy. So let's see how size fits in with that. Na and Mg are side by side on the periodic table. Mg is further right, so this is the smaller of the 2 cations. If I look at fluorine and chlorine, fluorine is higher up, so it's the smaller of the 2 anions. So both size and charge are going to help MgF2 have the greater lattice energy. So in this try it, I have, my first question is very similar to the example I just worked, so I'd encourage you to pause this and see if you can solve this on your own. And I'll go ahead and continue with my solution. So Kf and RBF, F is really going to be a non-factor because it's going to be the same size and same charge for both atoms. K, when I find it, I see it's in family 1. It picks up a +1. RB is also in family 1 and picks up a +1. So charge is the same for both. So it must be about size. So if I look, K is higher in the family, making it the smaller cation. RB is lower, it's going to be bigger. So Kf will have more lattice energy. With SrCl2 and MgO, I find strontium and see that it's in family 2, so it's going to give up 2 electrons. Chlorine can only take 1 or pick up a -1. Over here, Mg has a +2 and oxygen has a -2. So charge is going to give MgO a greater lattice energy. But we'll also double check size and make sure that size doesn't have the opposite effect. So if I compare strontium to magnesium, magnesium is higher in the family, so it is the smaller cation. And when I compare oxygen and chlorine, they're probably going to be very close to the same size because when I look at them, oxygen is further left but higher. Chlorine is further right but lower. So based on the Mg being smaller and the charge of O being greater, it would be most likely that MgO is going to have the greater lattice energy. My second question asks which compound in each pair would have the higher melting point? Well, melting point is when you go from a solid to being a liquid. So a stronger bond is going to increase your melting point. So that means Kf with the greater lattice energy is going to have a higher melting point or take more energy to melt. And MgO, also with the greater lattice energy, should have the higher melting point.